Go through the respiratory system. I know that we have already gone over anatomy in lab, and we even did the spirometers in lab, which is sort of physiology, but I still want to go back through the anatomy with you. Number one reason, that helps you get ready for your practical as you hear it and we point things out. And also, as we go through the anatomy in lecture, it's always a little bit different than it is in lab. In lab, it's just, this is where something is, and that's what's important. But in lecture, we need to really look more at why we do different things and what each of those anatomical structures is there for, why it's located where it is. As we begin, we've got to get some terminology under control. We've got to understand the difference between 5 processes. All 5 of these processes are not technically processes of the respiratory system, but you got to understand them to understand how the respiratory system works. Okay? Number one thing, the respiratory system's job is to get oxygen in, get CO2 out. Okay? The respiratory system's job is not breathing. Breathing is how the respiratory system accomplishes what it's trying to do. Okay? In actuality, we could say you don't really have to breathe to be alive. If we could just infuse oxygen into our body without our lungs inflating and deflating, you could still live, as long as you had a way of getting the oxygen and the CO2 out. Okay? So breathing is just the mechanism we use to accomplish what's required. Number one process that we've got to talk about with respiration is pulmonary ventilation. That is simply inspiration and expiration. Breathing in, breathing out. That is how we get the oxygen in and how we get the CO2 out. But that's not the only thing involved there, right? Is oxygen the only thing we breathe in? No. You breathe all kinds of stuff in. And we're not even talking about bacteria and dust. You breathe all kinds of gases in. There has to be a way for your body to know that the oxygen is what it needs. Okay? Once we've completed the first part of pulmonary ventilation, then we can do what's called external respiration. And to me, that's the most key part of the respiratory system's job. External respiration is the oxygen that is inside of your lungs going into your blood. At the same time, the CO2 from your blood is going into your lungs, so you can then breathe the CO2 out. Okay? So, I know it's not going to fit on there, so let me just kind of draw you a little bit of a schematic, real cheesy drawing, just so you can kind of see what I'm talking about. Okay? So if we have our lungs, the air going in and out of our lungs, that is pulmonary ventilation. Simply that movement in and out of the body. Okay? External respiration, let me draw a blood vessel underneath right here. Okay? External respiration is when oxygen goes out of the lungs into the blood, and when CO2 goes out of the blood into the lungs. So this is the area where that external respiration is going on. Okay? That is going to be probably the hardest part for you to understand as you start studying and we start going over things. There's a lot of driving forces that determine the movement of the gases this way. Okay? You could keep breathing air in and out of your lungs, but if the oxygen and the CO2 quit going in the correct direction, you would die, even though you were still getting air in and out of your lungs. Okay? If you start giving somebody CPR, are you breathing oxygen into their lungs? No, what comes out? CO2, right? When you give them mouth-to-mouth, you're breathing carbon dioxide into their lungs. Okay? We'll talk about why that works. But just because you're breathing in and out, that doesn't make them come back to life, right? They may still die even if you're giving somebody mouth-to-mouth. You've got to have this exchange down here. That external respiration is the key to keeping somebody alive, keeping that flowing in the correct direction. Okay? The other 2 parts that we need to have occur for respiration to happen is not really the respiratory system doing it. It's the cardiovascular system, the blood. Once we get the oxygen into our blood, we got to transport it through our blood to where we need it. Right? If I'm walking around my muscles in my legs are working, right? That's where I need the oxygen. So if we draw you a cell down here at the bottom, and assume that's the tissue or the cell that needs the oxygen. Once the oxygen has traveled and it gets here, the oxygen comes out of your blood, goes to that cell. CO2 at this point will enter the blood, and then the CO2 gets transported back. Okay? So do you see how it's one giant cycle, right? The movement through the blood is transport. This cycle of oxygen and CO2 exchange, this is your internal respiration. So does that make sense to everybody? Don't just think of it as I breathe in, I breathe out. Okay? It's the entire cycle that's going on. Pulmonary ventilation brings air in. External respiration puts oxygen in the blood. Blood transports oxygen to the area in the body it's needed. Internal respiration puts the oxygen into the tissue. Then internal respiration takes the CO2 from the tissue into the blood. It's transported through the blood. External respiration takes CO2 out of the blood, puts it in the lungs. Pulmonary ventilation brings it out. Okay? One giant cycle occurring over and over and over again simultaneously. This last process is called cellular respiration. And I don't even know if your textbook points it out to you, but I think it's a pretty important thing for you to realize that's going on. Why does this internal respiration have to occur? Why do we need to get the oxygen to our cells? Why do you need oxygen in your body? Uh-oh. We all know we got to breathe oxygen, right? To make ATP, okay? Even though a lot of teachers don't ever put that together, you just learn all those pathways and oxygen's at the end of it. This cell right here needs oxygen because oxygen is a key part of making energy. Why is this CO2 released right here? It's a waste product of energy production. Okay? So this little cell down here in our little cheesy drawing, that is a cell that's actively making energy. That's a cell that's actively doing something. So it needs the oxygen. It's making the CO2 waste product that has to be taken out of the body. Okay? Does that make sense? Okay? All right. So now let's go through our anatomical structures, kind of starting to talk about what each one of them does. As we go through them, we're going to categorize them. Is our structure we're talking about part of the respiratory zone or the conducting zone? Most of your structures are going to be part of the conducting zone. The conducting zone is just a set of structures that allows the air to pass from the outside of the body into the inside of your lungs. Okay? You aren't doing anything to the air other than maybe cleaning it or warming it, something like that, while it's in the conducting zone. You do not really get the oxygen out of the air until you get down towards the very bottom of the lungs, and that's going to be the respiratory zone. The only structures that are part of the respiratory zone are respiratory bronchioles and alveoli. Okay? And so we're going to go through all of them. We're going to start conducting zone. We're going to start at the top, follow the air all the way down. Okay, so this is just kind of our overview. Now let's blow it up a little bit. First, let's talk about the nose and your sinuses. That's the first place that your air has to go through. Okay? Does your air have to go through your nose? No, it can go through your mouth, right? But we're going to ignore that because air would actually be dirtier and not quite as ready for your lungs if it goes through your mouth. The best way to breathe your air in is through your nose. So we're just going to go through the nose, right? If you're exercising and you get out of breath, what are you supposed to do? Breathe through your nose, right? And you start huffing and puffing out of your mouth. That's not good. Proper way to breathe is through your nose, okay? All right, so here's our nasal cavity. If air is going to come in, air has to go through your anterior nares, which would be your nostrils, into the nasal vestibule, which, as I said in lab, your vestibule is just the space inside your nose. Stick your finger in your nose, your finger is in your vestibule. It's just the area. Okay? In your nasal vestibule, you have nose hairs. What are nose hairs for? trap dirt and particles, right? Turn it into a booger, you can pick it out, all right? That's one of the first parts that is there to help clean things that go into your nose. As the air then goes further in, the air then flows over these folds. The folds are called concha. This would be the inferior concha, the middle concha, and the superior concha. The little gaps underneath the folds, the little crypts underneath, those are called meaty. Underneath your inferior concha would be your inferior meatus. Underneath here would be your middle meatus. Underneath here, your superior meatus. The purpose of these folds is to increase the surface area that your air has to flow over. Makes your air stay in your nasal cavity a little longer. As your air is flowing over that, you're going to keep cleaning the air because there's mucus in there. All right? It's ciliated, pseudostratified columnar epithelium. Makes mucus, right, from A&PII. Y'all remember that. Okay, so we're going to keep cleaning our air. At that point, we also moisturize the air because we need it to be good moist for the physics of our lungs. We're going to talk about later to work correctly. Okay? In addition, this is where we begin to warm the air. The air outside is always going to be pretty much lower than the temperature inside your body. Very rarely does the air outside get warmer. Okay? Do you think it's important for the air to be warmed before you can breathe it in? Have you ever tried to do something when it's really cold outside and your lungs hurt? You ever tried to jog when it's cold or exercise when it's cold? Your lungs hurt because your air needs to be warm for your lungs to work properly. So as the air outside gets colder and that air goes in, your body can't warm it up as fast, and that's one reason it's harder for you to breathe when it's cold outside. Okay? At this point, our air also comes in contact with our frontal sinus and our sphenoid sinus. Those are also going to be there to help us clean the air because they can produce a mucus that can drain. Okay, we've all had sinus drainage before. We think of it as a bad thing. It is a good thing. Helps us to clear the air. Okay. Now our air is ready to leave our nasal cavity. It's going to go out the back, and this is what we call our posterior nares, or your internal nares. And the air is going to come out, and once the air gets right back here, this is now going to be the beginning of your pharynx, which we'll talk about next. Okay? Does that make sense? Okay. What would be the boundary of your nasal cavity? What's the superior boundary? Well, we did this in lab, and I think I'm mad at y'all. You still can't do it? What's this right here? The frontal bone. What's this right here? That's the ethmoid bone. What's this right here? Sphenoid bone. That's your superior boundary. What's your anterior boundary of your nose made of? What kind? Come on. Hyaline cartilage. That's why it's blue. Always in your textbooks, blue hyaline cartilage. Okay, inferior boundary of your nasal cavity. What's this bone? Maxilla, and this is the palatine bone, the hard palate. And then back here, soft palate. Okay? Y'all need to remember that stuff from A&PII 1. They're capable. Okay? Now this really has nothing to do with the physiology we're talking about, but just usually something kind of cute I like to throw in. Even though your nose doesn't help you produce your voice, it does alter the sound of your voice, right? I mean, I told you guys this in lab, right? If somebody has a teeny tiny little nose, guess what that's going to do to their voice? Make it really high pitched and squeaky. Okay? Somebody has a really wide, big nose, they usually have a much deeper voice, right? So not always, you know, it depends on the shape of their larynx and the way their vocal folds are made mainly, but it does have something to do with their voice. I just love to look at people when I hear a really annoying squeaky voice and look for that teeny tiny little nose. All right? Okay. Now let's keep going. This is our pharynx, showing you the 3 different areas. As we get into the beginning part of our pharynx, this is called the nasopharynx. At the back of the nasopharynx, we have our first tonsil. This is the pharyngeal tonsil. Okay? The nasopharynx is still going to be pseudostratified columnar epithelium. Still making lots of mucus, still cleaning the air that's coming in. Okay? As air continues to move down, air then comes into this area which is blue. This is the oropharynx. Now the air comes in contact with this tonsil. This is the palatine tonsil. Down here, this is the lingual tonsil. Okay? Once we get into the oropharynx, the structure of the epithelial lining changes from pseudostratified columnar to stratified squamous. Why do you think the surface needs to change right here? What comes through here besides air? Food, right? So it's rubbed a lot more. So you can't have that perfect pseudostratified columnar making lots of mucus right there because you constantly got food and saliva washing it out. So that's the only reason that area changes. Okay? It will become that columnar epithelium again as we get further down into the respiratory tract. Okay? Then the air keeps going. This part of the pharynx is called the laryngopharynx. Only reason it's called that is because it's behind our next structure we're going to talk about, and this is our larynx. Okay. Really important flap right here called the epiglottis. Talk about it more when we get to the digestive system. This little flap determines, it's kind of the switch point, determines which way things are going to go. When you're just breathing, doing normal things, that epiglottis is up like it's shown in the picture. So air can come in and air can go pretty much both ways. It mainly goes down the larynx, but it can go down the esophagus some. The only reason it doesn't go down your esophagus is because your esophagus is flat. So it's just harder for it to go down that tube. Okay? Whenever you eat and you swallow, your tongue depresses the epiglottis, pushes it down, and it covers up the opening of your larynx so that your food is forced down the backside. Okay? So it's a pretty important switch. What's the epiglottis made of? What kind of cartilage? Elastic cartilage. Good. Yeah, I know this was going to be A&PII 1 review day, did you? Yeah, I remember stuff. Okay, so that's our pharynx. Now let's look at our larynx. Your larynx is a very hard structure. It is a hard structure because it is surrounded by lots of different shaped pieces of hyaline cartilage. Okay? So why haven't we been protecting it with cartilage before? Okay? None of this stuff was surrounded by cartilage, right? What's it surrounded by? What's up here? Bone, right? All the other structures we've talked about so far have been surrounded by bone. Here's bone back here. This is a whole bunch of muscle in front of this. If you hit somebody hard enough in the face that you collapse their pharynx, they got a whole lot more to worry about than just not being able to breathe. Okay? But now that we've gotten down here into the larynx, this is really close to the front of the body, right? There's no bone, there's nothing protecting this in the front. If this gets collapsed or compressed, it's going to interfere with your breathing. So now that we're in the larynx, we got to start really protecting with lots of cartilage. Some of the most important pieces of cartilage are your thyroid cartilage. That's the big clump in the front that makes your Adam's apple. It's so large because it protects your thyroid as well as your larynx. Okay? But all these others are just giant pieces of cartilage. The cricoid cartilage is in the back. Thyroid cartilage is in the front, and the cricoid kind of wraps all the way around. Some of your medical procedures, you have to locate that cricoid cartilage to know where to do things. So that's the only reason I really point that one out. When they do a proper, I'll say it funny, tracheostomy. How do you say it? Somebody say it for me. Tracheostomy. Is that what it's called? Tracheotomy. Okay, I always say it funny. Thank you. That's where if you have a depressed airway or something blocking your airway, they actually will cut into your trachea and put a tube in so you can breathe. They have to locate that cricoid cartilage to find the bottom of the larynx. If you go above the cricoid cartilage, you may mess up the vocal folds. So that's why you have to go below. Okay? The neatest thing that our larynx does for us, other than just simply providing an airway for our air to go through, is on the inside, which I know these kind of look like dirty pictures, but I swear they're not. I know that's what y'all are grinning at while ago. This is what it looks like if you're looking down someone's mouth, okay? Up top, this is the very back of the tongue, okay? And if you're looking down, the inside of the larynx has this really thin lining that comes in, and then there's some teeny tiny little pieces of connective tissue that make up your vocal folds. Okay? And this is what we call our vocal cords. Okay? All that is, that's simply just two really thin membranes that almost touch each other. Okay? And if you've ever taken a piece of paper and held it up to your mouth and blew air right on a piece of paper, as that paper vibrates, what happens? It makes a sound, right? Okay? If you hold a piece of material, the harder you stretch the material, the sound's going to be different. That's exactly how your vocal folds work. They sit right up next to each other, and as you breathe in and out and air goes over that, sound is produced. Because as a little bit of air comes through, they vibrate just a little bit. You get softer sounds. You get higher pitched sounds when they vibrate slowly. When you have a loud sound come out, more air has to come through so that they come apart more and vibrate a little bit harder. Okay? The best way to prove that to you is if I wanted to yell, can I breathe out all the way and then yell? It's not possible, right? If I want to yell, the first thing I got to do is take a real deep breath in, and then I can yell. And even as I just stand up here and start teaching, sometimes by the end of it I find myself taking deeper breaths because I've just been talking longer. And in order to be able to keep my voice at a higher level so I can keep you awake, I gotta talk loud, I have to start breathing in a little harder just to get those vocal folds to vibrate like I need them to. Opera singers and even just anybody that's a singer, they have to train their voice. What they're doing, they're training the muscles around those vocal folds so that they can get the air to come out like they want to. Okay? Most of your opera singers, what do they look like? They're usually heavy-set people, right? Usually those type of people can have a little bit bigger lungs. They can usually breathe in a little bit more air. You don't have to, right? There's those like weird little kids that can produce that voice, but not really sure the physiological reason why they can do it. Most of your people that can sing, though, are usually bigger people because they can get more air in. They can force more air out, make a louder sound as it comes out. Okay? Anyway, so let's keep going. Y'all look bored. Well, there's lots of ways you could damage it. My father-in-law could not talk almost at all for several months, and it had nothing to do with his vocal cords. He had surgery on his cervical vertebrae. He had some messed up discs. They don't cut and go in through the back to do that because that's all bone back there. When you have surgery on your neck, they cut you in the front, and they move your trachea, your larynx, your esophagus. They just kind of move it to the side and work in your throat, and just the swelling that occurred from that damaged his vocal cords for a short period of time. Now, if it's like sometimes people that sing damage their vocal cords, and that's just from overuse. I mean, think about it. This is just a little membrane that's flapping, right? Somebody's singing all the time. That membrane's just going like crazy. It can almost gets like a flimsiness to it, and you have to let it rest so that it can firm back up, and you can get that sound to come back out. Okay? Usually people ask me, can anybody be trained to sing? I think anybody could be trained to sing better if you learn the proper way to, flow air through those vocal cords, but there's no amount of money or training that could make me sing. I'm just not one of those people that can sing. My child sometimes tells me to stop singing. So you sound bad when your child looks at you and says, "Mama, no." So we hum a lot at night. We don't really sing much. That's okay. Everybody's not meant to sing. I even mouth the songs at church because I'm scared the people next to me are going to think, "Oh, I wish she would stop singing in church." So I just mouth the songs at church. It's bad. Y'all laugh, but have you never thought at church, that woman needs to quit singing, right? I don't believe everybody makes joyful noise. I think some people just make noise. Let's see. All right. My child can't sing either. If y'all are interested, I'll show you the cutest video ever. I posted it on Facebook. We caught my child singing, she's just turned 2. We caught her singing Twinkle, Twinkle, Little Star the other night, and we've caught it on video. She screams. Twinkle, twinkle. It's the funniest thing. I'll show you that before y'all leave. It's really cute. So she can't sing either. It's genetic. All right. So now, larynx. We're moving on down. Now we're ready to talk about the trachea. This is still a structure towards the front of the body, not protected by bone necessarily, so we got to have cartilage to protect it. You need a patent airway. It's got to be kept open. The way you know you're moving from the larynx to the trachea is no longer do you have lots of misshapen pieces of cartilage like we saw in the larynx. The trachea has perfect concentric rings of cartilage. Remember when we did our pig dissection in lab, right? The way you knew it was the larynx, it was just kind of like a giant hard knot. That was the larynx, right? You knew it was the trachea when you could start seeing those perfect little rings. That's when it becomes the trachea, okay? Now, what this drawing is right here, this is a sagittal, horizontal section, right? Showing you this is the back side. That's what the esophagus looks like behind it. Pretty much just muscular. We're going to talk about it in the digestive system. This is your trachea in the front. The trachea actually has 3 layers. The inside layer of your trachea is called the mucosa. This is respiratory system, and we taught you in A&PII 1. Respiratory system was made of pseudostratified, ciliated, columnar epithelium, right? This is now where we finally get away and we get back to that correct type of epithelial lining. This is the main place where you have giant long cilia on the inside. And that you can, if you look closely at this picture, you can see there's some teeny tiny little cilia trying to point that out to you. This is where you make the most mucus in your respiratory system. You make all of this mucus through here so that anything that makes it past your nasal cavity, makes it past your sinuses, makes it past your tonsils, you do not want that in your lungs. So it has to be trapped in here in the trachea by all of that mucus. And then those little cilia are constantly wiggling. As they wiggle, that slowly pulls the mucus that has stuff trapped back up. When it gets to the top, you either blow it out your nose or you swallow it. When you swallow it, it eventually makes its way out. Okay? Just to try to get all my smokers, I love to try to give you reasons you should quit. One reason you should quit smoking is because some of the things and the toxins in the cigarette paralyze the cilia in your trachea. So that means anything nasty that makes it past your nose, there's no way to get it out of your trachea. A lot of times when people smoke, what do they develop? A smoker's cough. Yes, I know y'all smoke. That's why I keep looking at y'all. Right? You develop that smoker's cough. The smoker's cough is your body's attempt to get all that crud out because your cilia can't get it out. And that's why people develop that smoker's cough over time. At least you work out, so I have to say, you're trying to counteract that cigarette a little bit, right? Just at least tell me when I'm finished with school I'm going to quit. That's usually what everybody tells me, right? When I'm done with school I'm going to quit smoking. No, none of y'all are going to tell me that? Okay, that's fine. All right, so that was our mucosa, makes lots of mucus. Submucosas underneath, connective tissue. Adventitia, that is going to be your circular rings, okay? Rings of cartilage. What type of cartilage? Hyaline cartilage. Good. Just checking. All right, so now our air has finally made it all the way down to the bottom of the trachea. At the very bottom of the trachea splits into 2 parts. Because you got some that goes to your right lung, some that goes to your left lung. All the way through here, we're still in the conducting zone. We still haven't got to that respiratory zone, right? Hadn't said anything about getting oxygen into your blood or anything like that, right? All we're doing, pulling the air in, cleaning it, warming it up, just getting it ready, okay? Once we get to the bottom of the trachea and it splits, this entire area that's inside of the lungs, all these little branches are considered part of the bronchial tree. Okay, the whole thing is the bronchial tree. Each little branch of the tree is called a bronchus. Okay? The very first branch off of the trachea is called a primary bronchus. Once you get to right here, the primary bronchus splits again, right? Those are now going to be secondary or lobar bronchi. Okay? If we follow down to the bottom of this secondary bronchus, once it splits again, each of these pieces are now going to be a tertiary bronchi. Okay? Then when the tertiary bronchi splits again, and every subsequent split is considered a bronchiole. That makes sense to everybody? You follow it, and every time it branches, you give it a new name. Why? Because every time it branches, it does change structure a little bit. What's the main thing that happens to the structure as it splits? It gets smaller in diameter. Okay? Once it gets small enough in diameter, that's when you lose the cartilage that's around the outside of it. Because then it's getting so small and it's all the way on the inside of the lungs that it's protected a little bit more, so you don't have to have that cartilage on the outside of it. Okay? So it is changing as you go down. Okay? Once you get to these very tiniest little bronchi in the very terminal portion of your lungs, they get really small in diameter until you get to the point where you have this large grape-like structure at the end of each one. Okay? The little grapes, the little circular sacs at the end, those are each called an alveolus. Multiple, which you have millions of them, they're called alveoli. Okay? I'm trying to say that correctly because I have a respiratory therapist in one of my classes, and she corrected me the other day. I usually say alveoli, and that's apparently wrong. So I'm sorry, I'm a little southern. I like to say it that way. But I think it's alveoli, or I'm still probably saying it wrong. Okay, but anyway, those are your little sacs at the end. Now, they're always drawn to look like perfect little circles, like grapes. Not what they really look like in reality. In reality, they are almost a contractile structure. They're not going to always be giant, perfect circles. Now, they never deflate. If they deflate completely, that's bad. You can't do what you're supposed to do when you get the air in. So they do have to stay open, but they're very, very thin-walled little structures. They're filled on the inside by something called surfactant, which helps keep them from completely going down. Okay? And the best way to describe that to you, have you ever went to the store and had somebody blow up helium balloons for you, right? What do they do to that balloon before they blow it up? They stretch it out, right? Make sure it's good and stretched. Your alveoli are stretchy. They're already stretched. Then they take that balloon and they go put it on this little thing and squirt something in it, right? Before they blow it up. You ever notice that? What are they squirting in it? It's soap. Okay? It's a soapy structure. That's the surfactant. Because as that balloon starts stretching out, you don't want one part of it to get thinner than the rest, right? Because if one part gets thin, what's going to happen? It's going to pop. It's going to rupture. Okay? You have a natural soapy structure on the inside of all of these little alveoli in your body. That makes them stretch out evenly, contract down a little, but keeps them from deflating completely. Okay? So that's just called the surfactant on the inside. These are almost microscopic structures. Okay? Now in a human, they would be big enough that you would be able to tell the bronchioles have gotten super thin, but it's not going to look like that. It's just going to look like the end. You would have to look at them under some magnification to see the roundness of them. Okay? And they're also buried on the inside of the lungs. So you'd have to actually know how to properly dissect the lungs to even be able to see that. But on the little baby pig in lab, they'd be way too small. You'd never be able to see them. Okay? All right, so that's our little alveoli. The bronchioles that lead up to the alveoli have special names. Okay? The one that's actually connected to the little duct with the alveoli on them, that's called the respiratory bronchiole. The part that branched to become a respiratory bronchiole, that's a terminal bronchiole. The terminal bronchiole is the end of the conducting zone. Once you get here, where that little cursor is, to the respiratory bronchioles and the alveoli, that's the respiratory zone. Okay? So pretty much the rest of the time we spend talking about the respiratory system, we're only going to be looking at what's happening in the respiratory zone and the inside of the body. Because we've already said everything we needed to say about that conducting zone. It was just the structures getting the air in. Now we're going to actually talk about getting what we need out of that air into our body. Okay? So all we did was just breathe all the air in, and we got it to this point of the alveoli. Now we need to figure out how am I going to get the stuff I want out of that air. Okay? Now in my cheesy drawing, you all said you understood the air has to come from the lungs into the blood, right? Okay? In real life, do y'all see how there's kind of some lines drawn? It looks like some lines drawn and wrapped all the way around those alveoli. Those are capillaries. What's a capillary? It's the thinnest part of the blood vessel where you have gas exchange, right? Okay? So coming from the heart, let's put all this together. Coming from the heart, we had the pulmonary artery, right? The pulmonary artery branched, got smaller and smaller, became arterioles, into the lungs, became capillaries. We need to get the oxygen at that point, right? Those capillaries are wrapped around each of these alveoli. We're going to put some oxygen in that capillary, and then they'll become venules, go back, pulmonary vein, take that oxygen back to the heart so our heart can distribute it through our body. That make sense to everybody? Okay. We call the interaction between an alveolus and the capillary the respiratory membrane. Okay? So on our little drawing right here, where the external respiration occurs, that is the respiratory membrane. Okay? So I'm going to draw it a little bit bigger, and then I'll show you what it looks like in this picture so you can keep up. Okay? So at the very bottom, I have one alveolus, right? Wrapped around that alveolus, right next to it, there's going to be a capillary. Okay? We need the oxygen to go from the alveolus into the capillary, right? And we need what to come from the capillary into the alveolus? CO2. Okay? The respiratory membrane is simply the area right there where those two interact with each other. Okay? So as you read through in your textbook, and a lot of times they'll ask you on tests, especially the stupid standardized tests, the respiratory membrane is composed of. Well, you have to understand the respiratory membrane is where your lungs are making contact with your blood. So the respiratory membrane is composed of the epithelial wall of the alveolus. That just means the edge, right? The basement membrane of the alveolus. So what does that mean? Do you remember all the way back to A&PII 1 when we started talking about epithelial tissue? We said there were 5 characteristics of an epithelial tissue. You can tell the top and the bottom, the cells were always touching, and then one of the key characteristics of epithelial tissue was you always had a basement membrane. Remember that? The basement membrane was what all of your little epithelial cells connected to. Okay? So since this part of your body is made of epithelial tissue, you've got the epithelial tissue and the basement membrane of your alveolus. The wall of your capillary is also made of epithelium. So you have the basement membrane of your capillary wall and the epithelium of your capillary. Does that make sense to everybody? Because if I just tell you there's 4 parts to the basement membrane, most people just don't really understand where that fits in with anything else. Okay? All the basement membrane is, that's just part of what makes up the epithelium. The respiratory membrane is where the alveolus meets up with the capillary so we can have gas exchange between the two. Make sense? Respond. The whole thing is the respiratory membrane. The basement membrane is part of the epithelium. Make sense? The respiratory membrane is more of a functional structure. It's where they meet because that's where something important is going to happen. Right? Up until this point, all we did was breathe it in. Okay? And just like you all predicted, oxygen is not the only thing you breathe in. On Earth, there's actually a higher concentration of nitrogen gas in the atmosphere than there is oxygen. Okay? So what makes the oxygen go in? That's what we're going to talk about. This is the point where your body actually makes the decision. I want the oxygen to go in. I want the CO2 to come out. I don't want all that nitrogen to come in. I don't want all that CO2 to come in. I don't want all the sulfur gas. I don't want that other junk. I just want the oxygen to come in and the CO2 to come out. We good? Okay. All right. Last little bit of structure that we have, and then we get to talk about physiology, is the just outside structure of the lungs. Of course, our right lung looks different than our left, right? Why is that? The heart projects more into the left side of our body. The part of your lung that kind of looks like it's missing on the left is called the cardiac notch. It's simply just over time, over evolution, as our heart has pushed on that, you just don't have the lung right there, okay? So that means your right lung's bigger. It's got 3 lobes, superior, middle, inferior. Your left lung is smaller, so you just have a superior and an inferior lobe. On both lungs, you have an oblique fissure. On your right lung, you also have a horizontal fissure, okay? The bottom of your lungs are boundaried by a very important muscle called the diaphragm, okay? And then, of course, your rib cage is going to be anterior as well as lateral boundaries wrapping around your lungs, okay? There's also some important muscles in your ribs that we're going to talk about today and tomorrow, too. Do y'all remember what the muscles that run through your rib cage are called? Intercostals. There's 2 of them. There's external and internal. How do you tell them apart? Right, my students should know, right? External always goes this way. Internal always goes this way. Just like your obliques. External, internal. Intercostals. External, internal. Okay? We're going to use those to help us breathe. Okay? We'll cut the body in half. A horizontal cut. You can see, here's your lung. Okay? This is the bone and your body around the lung. There's a teeny tiny little space that the lungs sit in called the pleural cavity. There is a fluid in here called the pleural fluid. It's a much thinner consistency than your pericardial fluid. There is also some air inside of your pleural cavity. And if you've ever watched any medical shows, right? You got to keep the air inside that pleural cavity correct or your lungs collapse, and we're going to talk about all that as we go through. Okay? But I really like this picture. Even though when you first look at it, I'm sure you guys think it looks like nothing. Okay? So here's our heart in the center. This big blue thing coming out right here. Pulmonary trunk, right? What's this? Left pulmonary artery. Then it comes out into the lungs. Why does it branch so much? It's got to branch and get really thin, right? So it can become a capillary so that it can meet up. Okay, and then once you get your oxygen, that's when the red comes back in, becomes left pulmonary vein, goes back to the heart. Okay, we always got to make the connections between what we're learning about. Okay, all right. So now, let's get ready to talk physiology. To understand the physiology of the lungs, we are going to talk about an equation that some of you probably have learned if you've ever had a chemistry class in your life. Okay? Have any of you ever seen this equation? PV equals nRT. Have you ever seen that? Some of you are going, oh my God, really? Did you have a question? We're going to talk about it. Ask me next class. Okay? I got to explain a few other things first. Okay? This is considered the gas law equation. Okay? We're not going to work any problems or anything like that, but we are going to learn 3 laws that were derived from the gas law. What this gas law tells us is actually a pretty simple equation for us to use. The P stands for pressure. The V stands for volume. Okay. N's number of moles. That just means amount of gas you have. Okay. R is a constant. Means somebody with absolutely no life spent their whole life working on something and figured out you always got to put a certain number in there to make this work. Okay. If I remember, it's like 8.31 joules per mole per Kelvin. Okay. That's what you call it to me in chemistry classes. That's why that's stuck in my brain. Okay. You don't have to know all that. I was just telling you what it was. What do you think the T is? Temperature. Okay. We are not going to fool at all with that side of the equation. Okay? We are going to be looking at how pressure and volume are related to each other. Okay? And it's actually a fairly simple correlation. Since they're on the same side of the equation, they're always opposite of each other. Okay? Anytime you have high volume, you have low pressure. Okay? Anytime you have low volume, you have high pressure. See, that's easy, right? When I first wrote an equation on the board, y'all all freaked out on me. I could see y'all doing it, okay? It's not something hard. This is just some guy worked it out to prove to us that pressure and volume are opposite of each other. Now, as we go through all these discussions, though, for the next day or two of class, I said we're not worried about the other side of the equation, right? So that means we're always going to assume the temperature is staying the same. Because if you change something on this side of the equation, that would change the other side, right? So we're just going to assume temperature is constant as we talk about it. And then when we're finished and we all understand, we'll talk about how temperature can affect different things. Okay? But for the first part, we're just going to deal with pressure and volume. So let me give you a real-life proof that pressure and volume are always opposite of each other. Okay? If I take, what does pressure mean? Let's start there. Let's make sure everybody understands that. What is pressure? Okay, so it's like pushing on something, right? If I push on my arm, I'm increasing the pressure that I'm putting on my arm. Okay? So what does pressure mean as far as gas molecules? Is there a pressure in this room right now? There is, right? Because there's gas molecules in this room. The pressure comes from the gas molecules moving around, pressing on the wall, pressing on you. Okay? Is the pressure in this room right now real high? No. You can't even feel the gas molecules pushing on you, right? Okay. What happens to your tire as you put more and more air in it? The pressure goes what? Up. Okay. All right. So let's take another way of looking at it. Let's pretend we're blowing up a balloon. Okay. If I have a balloon that is deflated, the volume is low, right? Volume's just the size of a container, right? As I start blowing air into the balloon, what am I doing to the pressure? I'm putting air into it, right? How does the volume of that balloon respond to all that pressure? By swelling, right? It has to grow. The bigger the balloon gets, the more air I can put into it, right? Okay? As I increase the volume of the balloon, the pressure goes down so I can actually put more and more air into it. Okay? Does that make sense to everybody? See, you understand pressure. All you had to do is think. You've all blown a balloon up before, right? Okay? That's how it works. You have to increase the volume of the balloon to be able to put more pressure into it. Okay. That makes it burst. No, I mean, yeah, because it has a limit. Your lungs do too. You could theoretically make someone's lungs explode if you forced air and air and air into them and never let any of it come out. It would be the increase in pressure would eventually make it explode. But then you start talking about elasticity, and so that kind of changes it a little bit. Okay? All right, so if you understand how a balloon blows up, then you should be able to understand how your lungs work. Okay? When I breathe in, what am I doing with air? Putting it into my lungs, right? So what must the size of my lungs do in order for that air to go in? Expanding it bigger, just like the balloon, right? What is going to happen to the size of my lungs when I breathe out? The volume's going to go down. Okay? So see, you already understand this. You just have to put it together. And the hard part, you have to put it in A&PII terminology. Okay? So we got to learn 3 definitions. atmospheric pressure, intrapulmonary pressure, and intrapleural pressure. Okay? Atmospheric pressure, what's that? Pressure of the atmosphere, the pressure around your body. Okay? At sea level, the pressure around your body is 760 millimeters of mercury. That's just one way they measure it. The other way they measure it is in atmospheres. Now, sometimes when people see those units of measure, they don't like that. Okay? You know how much you weigh, right? You weigh that many pounds. Does it change it if I say, okay, well, you weigh this many kilograms? No. I mean, it changes the number, but it's still, you still weigh the same, right? Okay? That's just two different ways of looking at a measurement, okay? We're not going to even really look at numbers, but we're going to talk about, do we have a negative pressure or a positive pressure? So if anything goes below what it is in the atmosphere, it's a negative pressure. Anything goes above, it's a positive pressure. Okay, so we're just going to kind of do positive and negative instead of talking numbers, because numbers get confusing. Okay? Do you think what the pressure is around your body affects how your lungs work? Yes, right? Have you ever went to the mountains and tried to just walk around? All of a sudden you're winded, and normally you can jog. Right? The difference is the pressure around you has changed. Okay? A lot of athletes, when they're training for Olympics or big-time training events, they have to go somewhere else if they're from here. I have a really good friend that runs marathons. She is getting ready to run one in Boston. Okay, even though Boston's not in the mountains, it has a very different atmospheric pressure than we do down here in South Mississippi. So she's been having to run marathons in Chicago. She did one in Colorado last weekend, just so she can get her lungs used to the different atmospheric pressure. So she's able to do it. Okay? All right. Intrapulmonary. What does pulmonary mean? Lungs. Intra. So the intrapulmonary pressure is the pressure in the lungs. So actually talking about the pressure in the alveoli. This is the one that we're going to watch change as we breathe in and out. Right? You all said you understood how the balloon worked, right? You said, as I breathe in, what's going to happen inside of my lungs? I'm pulling more air in, so the pressure's going to do what? It's going to go up. The lungs get bigger, the pressure goes up and down, right? So you're going to see positive and negative intrapulmonary pressures. That one's the one that's going to change. Is atmospheric pressure going to change as I breathe in and out? No, right? Just what's in your lungs is going to change. The intrapleural pressure, what does pleural mean? The pleural cavity around the lungs, right? Your intrapleural pressure always has to be negative. So what does that mean? What does negative mean? Below atmospheric pressure. Okay? It is going to change a little, but even though it changes, it can never equalize or become positive. If the pressure around your lungs ever equalizes with atmospheric pressure or becomes positive, your lungs collapse and can't breathe. Okay? That always stays negative. So even though some of you are starting to probably think that God is starting to sound complicated, it's really not. We're only going to be looking at how one of these changes. We're just going to understand atmospheric pressure is what it is. It can't change. Intrapleural pressure may change some, but it just has to stay negative. We're going to look at how things change on the inside of the lungs. Okay? Go ahead and get familiar with these little abbreviations, because that's kind of the way you're going to see it as we go through. Okay? ATM, atmospheric, PUL, pulmonary, IP, intrapleural. Okay? I didn't come up with those. That's the way it just is kind of done. Okay? All right. So now what I want to do is, I don't want to get into this too much, but I want to kind of go ahead and tell you that you need to prepare for class next time. And here's what I want you to do to prepare for class. I want you to be able to tell me what Boyles Law is. Okay? And it's in your notes, and this is what we're going to talk about next time. I want you to know what Boyles Law is. Dalton's Law and Henry's Law. Law means it's a physics principle. Every single one of these laws comes from the gas law, okay? It's just accepted reactions. And what I want you to do, I don't want you to just type this into Wikipedia and write down an equation. I know the equation. This is Boyles Law. P1V1 equals P2V2. That means nothing for you to memorize that, right? That's just some letters. That's not what I want you to do. I want you to actually just read a little bit and read what that law tells us. Put it in words. Don't memorize a definition. That's what most people hate about chemistry and physics class. Don't just memorize equations. You know, read the words. Learn what something actually means. Okay? And in our next class, we're going to go through those 3 laws. Okay? And we're going to learn the difference between quiet breathing and forced breathing. What do you think the difference between that is? We did that in lab a little bit, right? What's quiet breathing? Your regular old normal breathing. That's what we're all doing right now, right? What's going to make it turn into forced breathing? Exercise. Something that gets you out of breath. That's going to make forced breathing. Is that going to change the way you breathe? Yeah, because when your body switches to forced breathing, what's it trying to do? It's trying to get more oxygen in, or more often, it's trying to get rid of CO2. Hyperventilation is not your body trying to get more oxygen, it's trying to get rid of CO2. And so we're gonna try to talk about some of those things and make it a little bit more realistic. But you gotta understand those 3 laws for any of the other stuff to make sense, okay? Can y'all handle that? All right. Okay, yeah, I can do that. You don't have to stay if you don't want to.